As this is going to be our last lesson in terms of this unit on applications of integration. So we're going to talk about the same kind of thing we did from the last lesson, looking at finding volumes of the revolution of these shapes, and they turn into different types of solids of revolution. And so we've already talked about two of them from the last lesson, the disk method and the washer method. And today is going to be called the method of cylindrical shells. Okay, so in the book and in your calculus for dummies, it goes through kind of how this came about and the proof behind it and the work behind getting to this formula. But as I say in most of my videos, I'm just going to be focused on actually applying these different calculus topics. So we're going to be focused on using this formula to find the volume. Now, just one thing that I want to make sure that's kind of unique or different about this is obviously the formula is different, but the way that we rotate is a little different. So on the previous two methods, the disk and the washer method, we focus on rotating about the x-axis or the y-axis. But you'll notice that we're going to be talking about lines on the left and the right where it says x equals a number and x equals another number. But we're going to be rotating around the y-axis. So it's a little bit different than how we did this on the last one. So let me show you. All right. So here we have the function 1 over x. Okay, so right there, 1 over x. And we're looking at that area between 1 and 3 that's below this curve. So again, if it was a problem just like this in this graphic in part A, that would be something that we would have done in unit 5. But since we're going to be revolving this area under the curve around the y-axis, it creates this cylindrical shell. Okay, so I'm going to write down my formula, which is the integral from 1 to 3 of 2 pi x times, and my function is 1 over x. Okay, again, if you need to refer back to it, please refer back to it. Now, when you do this, I'm going to pull that 2 pi out front, right, because those are just constants. But x times 1 over x is actually just going to cross out and leave me with dx, right? And it may have actually been a while since you've done this, but the integral of just 1 dx is going to actually be just x. So I'm going to evaluate that at 3 and 1. So f of 3 minus f of 1, and whatever I get there, I'll multiply by 2 pi. So that's going to be 3 minus 1, which is 2. All right, so I'm going to multiply 2 times 2 pi and get my volume is 4 pi units cubed. All right, so that's it for the first one. Let's try another one. Same kind of process. You'll notice here is what it looked like a unit ago. Now we're taking that and rotating it around the y-axis to look like this new shape. We want to find the volume of that. So it's going to be the integral from 0 to 2 of 2 pi times x times 2x minus x squared dx. I'm going to move the 2 pi in front, distribute that x to get 2x squared minus x cubed. Do my integral. So I have x cubed, but I want 2 to be in front of it when I differentiate. So I'm going to put 2/3. And then I have x to the 4th power, but I want to do the reciprocal, so I get 1 when I differentiate. All right, so that's it. I'm going to evaluate it at 2 and 0. Again, since one of them is 0, you really only need to evaluate at 2. You can show the work for both if you want. So 2/3 times 2 cubed minus 1/4 times 2 to the 4th power. That's going to be 16/3 minus, 2 to the 4th power is 16, divided by 4 is 4. Getting common denominator, 4 becomes 12/3. 16/3 minus 12/3 is 4/3. Again, that's not the answer, right? You still need to multiply by that 2 pi that I moved out to the front. So my volume is going to be 8 pi over 3 units cubed. Again, feel free to use decimals if you'd like to get the actual volume. All right, so that's it for this example for 6.13. Okay, now let's talk about something a little different here. Okay, so the only change here for this next one is that instead of looking at your bounded area between your x values and rotating around the y-axis, now we're going to switch it, do our bounded area with y values, but rotate it around, revolve it around the x-axis. So just a little bit of a twist. Again, this problem you'll see is pretty straightforward because they've already written it in terms of y, right? But you'll see on some of the review questions that we do for this test that the AP exam might require you to do some rewriting of the function, okay? All right, so I'm going to do the integral from 0 to 4 of 2 pi times y times 2 times the square root of y dy. Okay, I'm going to move the 2 pi out front. I'm going to distribute and get 2 times y, and let's see, 1 times y to the first power times y to the 1/2 power is y to the 3/2 power. Actually, I should have, you know what, before I do that, let me go back to this. I'm going to move that out and actually make it 4 pi outside because 2 times 2 is 4, and move it outside as well. Okay, so here we go. Let's find the antiderivative. So if y to the 5/2 power, I'm going to put 2/5 in front. Remember, all this is going to be evaluated at 4 and 0, and then I will multiply whatever that is times 4 pi. All right, so let's do 2/5 times 4 to the 5/2 power. I don't need to do 0 because that's going to be 0. So that's going to be the square root of 4 is 2. 2 to the 5th power is 32. 32 times 2 is 64/5. All right, but again, I'm not done. I got to multiply that by 4 to get 256 pi over 5 units cubed. Again, if you're like, whoa, how'd you do that? No worries. Just go to Desmos to find what that is as a number. Okay, let's keep going. Now, this next one is talking about revolving it around a line instead of a y-axis. It's got a line. So you'll notice in the formula we used earlier, it was a to b 2 pi times x times f of x dx. So really all this is going to change is what's happening with this x. And the way that the book talks about it is if your line is the opposite of k, where k is a positive constant, then that's going to change what happens with that x, and it's going to be x plus k. So this right here would be replaced by x plus k. So in this problem, it says we're revolving around the line x equals -1, so my k is actually going to be +1. You got to think opposite. So I'm going to write x plus 1 when I do this. So watch what happens when I write it. Very similar. The integral from 1 to 2 of 2 pi times x plus 1 times my function, which happens to be just x dx. Okay? So I'm going to move that 2 pi in front. And I have x plus 1 times x, which is x squared plus x. And I can find the antiderivative of that. So it's going to be 1/3 x cubed plus 1/2 x squared. All of that evaluated at 2 and 1. And don't forget, I will be multiplying that by 2 pi. I'm going to go to decimals for this one because one of them is not 0. So I do have to show or do a little bit more work when it comes to this evaluation. All right, so I have 1/3. 1/3, let me put this in parentheses, times 2 cubed, make sure I got that, okay, plus 1/2 times 2 squared. All of that minus the same thing for 1. 1/3 times 1 cubed plus 1/2 times 1 squared. All right, so there it is as a decimal. I'll put it as a fraction, 23/6. So if I do 1/3 times 2 cubed plus 1/2 times 2 squared minus 1/3 times 1 cubed plus 1/2 times 1 squared, I get 23/6. But again, I need to multiply that by 2 pi. So my volume is going to be 23 pi over 3. units cubed. Okay. Now, one more before we get into kind of the putting it all together section of this lesson. So now it says we're going to find the distance between, or the area between two graphs or between two curves, and we're going to rotate it around that y-axis. Okay, so it's going to kind of involve a little bit of stuff that we did in the previous unit. So all that I'm going to do is I'm going to do the integral from 1 to 4 of 2 pi times x times, now watch this, you'll notice the square root of x is above, so I'm going to put that, minus the one that's below is 1 over x dx. Okay? So again, kind of similar to stuff that we did in an early lesson. So we have 2 pi coming out front. We've got x times the square root of x, which we did earlier with y. So x to the first power times x to the 1/2 power is x to the 3/2 power. And then x times 1 over x is actually just going to be 1. So we integrate, we get x to the 5/2 power times 2/5 minus x, evaluated at 4 and 1. All right, so I think I can do this one mentally, but if you're worried about it, you always just use Desmos. So 2/5 times 4 to the 5/2 power minus 4 minus 2/5 times 1 to the 5/2 power minus 1. Okay, so square root of 4 is 2. 2 to the 5th power is 32. 32 times 2 is 64/5 minus 4. This one's going to be 1. That's 2/5 minus 1. So let's see, 4 over 1, so multiply that by 5 over 5, gives you 20/5. 64 minus 20 is 44/5 minus, there will be 2/5 minus 5/5, which is negative 3/5. That becomes plus 3/5, so I get 47/5 times 2 pi. So 47 times 2 is going to be 94 pi over 5 units cubed. All right, so that's it for the area for that solid of revolution. Okay, so now to the last part. The last part is kind of organizing all this stuff in a chart about kind of when is the best time to use each of these methods. Key thing I want you to focus on is the first two, right? It's really this row here. This row will kind of tell you a little bit about your guide of where you can go, right? If we have a cavity in the center, then we're going to kind of rule out the disc method. And if we don't have a cavity in the center, we really don't need to use the washer method. So that's kind of the first thing I ask myself. And then I'll show you with the shell method, with some of these, that you've really got two options, and it's up to you which one do you think would be the simplest to do. Okay, so let me show you two here. Here's the first one. So we're looking at the region that's bounded by these two lines, x and 2 minus x. And you'll notice that if we were to do this with just finding the area under the curve, like in this one, like we did in Unit 5, we would have to actually separate this into two of them. We'd have from 0 to 1, where your y equals x is the one that's bounding it, right here kind of splits it. And then 1 to 2 is where 2 minus x is really what you're looking at. So that would be the disk method. So let me show you kind of what I would write there. This is for the disk method. So if I use that formula where it says the integral from a to b of pi times the function squared, I'd have the integral from 0 to 1 of pi times the function would be x squared dx plus the integral from 1 to 2 of pi times the function is 2 minus x squared dx. This really doesn't seem like it'd be that big a deal. Like, I have no problem. None of us would have any issues doing it. But let me show you what happens if you did the shell method. All right. So the shell method, because we're rotating and revolving around the x-axis, we actually have to change this to be in terms of y's. Remember, that's the new thing here, is that if you're going to integrate with respect to x, you actually have to revolve around the other axis for the shell method. So since we're revolving around the x-axis, I need to rewrite these two functions here in terms of y. Now the first one, y equals x, that's already good to go. But if I rewrote, right, so if I wrote y equals 2 minus x and moved that x over to get y plus x, and then if I move the y over and get 2 minus y, that's what I would use for the shell method. All right, and again, we're talking about the y values. You'll notice I'm going from 0 to 1 on the y values. So it'll be 0 to 1 of 2 pi, all right, and then times y. And then don't forget, when you look at this, you're looking at for when you're revolving around the x-axis. So in terms of y, we're using the one that's on the right minus the one that's on the left. So the one on the right is the blue one, which is 2 minus y. So it's going to be 2 minus y minus the one on the left, which is just y dy. Clean that up a little bit. You get 2 pi times y times 2 minus 2y. And it's up to you which one you'd want to choose. Both would give you the same answer. And I don't have to do these. It says do not evaluate the integral, but some students might choose the second one because there's only one integral. Some students might choose the first method because even though there are two intervals, they are in terms of x, and that might be something you're more comfortable doing. Okay, so those are the two methods there that would work. Let's do another one, and then we'll be done. All right, so this one, we're revolving around the x-axis. You'll notice there's no cavity, so I don't need to use the washer method. It rules that out. So I'm going to start with the disk method. All right, so we're talking about the integral from 0 to 4 of pi times our function squared. So 4x minus x squared dx, okay? And if you wanted to, you could do the the shell method, all right? But again, because we're rotating around the x-axis, I'd have to rewrite this in terms of with letter y's. And that might be a little confusing because we've got somewhat of a complicated quadratic here. So I think even though we could show what that is, there's really no reason to do it because ultimately this seems pretty straightforward. It's one integral. So you've already done many practice problems like this. So I think the disk method will be the way that I would go here. Okay. Anyway, so that's it. Try some of these practice problems and we'll get into reviewing for what it looks like on the AP exam.